So what is hazard? So something which is dangerous. Whenever we have say circuits, how we call this as it is an unwanted switching transients due to the propagation delay of the given circuit. Or in short, you can also add a point like it is a temporary false output. Got it? So now we can see the types. There is basically three types available for it. There is three types. First one is static hazard. Second one is dynamic hazard. Third one is essential hazard. Okay. So this static hazard is further divided into two types. One is static 1 hazard and another one is static 0 hazard. Here I will just try to tell some glimpse about what is static, dynamic and essential hazard. Then we will go to the main topics one by one. And in our lectures we are just going to focus this part, and I will be asking you to do this one. Then dynamic focus I will focus a lot. Then finally I will focus with respect to the essential hazard, and mostly I gave this as an assignment, so you will be asked to do this as an assignment. Okay. So first I will tell about the idea about what is the static 1 hazard. So actually I added a point like temporary false output. So actually my output should be 1, but it changes to 0 and comes once again to 1. This is called static 1 hazard. Actually my output should be 0, it goes to 1 and comes back again to 0. This is static 0 hazard. Actually my output should be 1, but it goes to 0 and it comes back to 1, and once again it goes to 0, then it is coming back to 1. So this is called dynamic hazard. Likewise essential hazard is, if you see, it normally occurs in asynchronous sequential circuits. So why this is normally occurring in asynchronous sequential circuit is, you take any random circuit. If you see in this circuit diagram, this input I have fed in here, here and here. So you can't expect always the propagation delay to occur same. And depending on the length of the wire and depending on the delay available in the gate, there is a high possibility like different delays may occur in different path, which is having a common path of this one. So this is called as essential hazard. So to eradicate it, for example, if it is having 1 nanosecond, this is having 3 nanosecond, this is having 2 nanosecond delay, to eradicate it, we should make sure to bring all to either 1, 2 or 3. So which means 1 nanosecond, 1 nanosecond, 1 nanosecond. So if you bring it like that, this essential hazard can be rectified in asynchronous sequential circuit. And do remember, in synchronous circuits also, transition just occurs like this. Since clock is available, this clock will maintain it and it doesn't going to affect lodge in the stable state of any particular circuit. But when you take asynchronous, it is not like that. A small change like this will drastically change your stable state. So this source and all will have a major influence with your asynchronous circuits only, not mostly with your synchronous circuits. Okay, that is one important key point. I'm going to start on with a circuit. Input like 1 1 1. What will be your answer? 1 1 is 1 and 1 1 is 1 here. 1 1 is 1. Then here 1 will be converted to 0 and 0 into 1 is 0. So 0 plus 1 is 1. This will be your answer. Suppose if I change this to 0, 0 1, 0, right? So 1 into 0 is 0 and 1 and 0 into 0 will be converted to 1. So this is already 1. 1 into 1 is 1. So 1 plus 1, once again the answer is 1. So this is what you normally you will tell the answer, right? But here what I am going to do is I am going to consider the delay in each circuit. So how this delay in this asynchronous combinational or asynchronous circuit, how this delay, because each gate have a delay, each wire also have a delay. This is what we call this propagation delay or whatever we call. So this is the thing. So now I am going to consider this and I am going to design. So for that reason I will take the delay on each case as 1 nanosecond, 1 nanosecond, 1 nanosecond. So these two circuits will give parallel output. So this part of the circuit, these two comprises, I will take a stage 1 for understanding, which will be useful in designing. Then this part, it depends purely on this output and this input, right? So this part alone I will take as stage 2 and this part I will take as stage 3. Once again I am writing your inputs over here and I am writing the intermediates x1 and x2 over here, then y over here. So I am going to show this how it is occurring in each time period. So to represent that I am going to give T1, T2, T3, T4, T5, T6. Okay. Then I will split that up. I will replicate in graph manner. So like this if I represent it is 1, like this if I represent it is 0. Okay. So try to get this. So initially I have designed like 1 1 1 1. So at that, so when I give this one, the entire delay I am considering as 1 nanosecond. So it is immediately after this period, after a certain period, it is giving the output like 1 for y. X1 will be previous state here. X1 1 into 1 is 1. X1 is sorry 1 and x2 is it's 0. So 0 1 and this one is 1. So here I am not considering it in the sense just switch off, this term switched off. Once I implement this, it is activated and show the. Now I am going to change this B alone to 0. Remaining all will be maintaining in 1 itself. This also will maintain in 1 itself. So now we can see what is happening in each part. So when I convert this to 0, normally your answer y will be 1 that we saw previously. But now here what I am going to show stage by stage what is happening. So in this first stage 1 into 0 is 0. So your x1 value is 0. X1 value is 0. So I can't mention the 0 over here. So my x1 value is 0. Okay. Now 0 is converted to 1. But this is happening in the first stage. So this 0 will be converted to 1 and this 1 into 1 is 1, which means your x2 value will become 1 after 2 nanoseconds. So 1 2 changes over here after 2 nanoseconds. So here what will happen is the output will change to 1. x2 will change to 1. Previously it is in 0 only. So like this. So that's enough. And now we come to the output part. We can calculate these because output is a combination of x1 and x2. So x1 is x1 is what, yeah, 0, and this is 0, so your output will become 0. Then x1 will be 0 here also, then 0 output is, your output will become 1. So actually your output should be always 1, but due to the temporary change which has happened to this delay, your output temporarily goes to 0, then comes back to 1. This is what I said previously, like this, 1 comes to 0, then to 1. Same thing happening. This is called static 1 hazard. Okay, I think you got a very clear idea. So this is called static 1 hazard. Now we can see the ways of eliminating the static 1 hazard. Okay, so a given circuit is given, so we can first find the expression of it. So y is equal to x1 plus x2. So your x1 value is a into b, and your x2 value is b dash into c. So see, from this I also like to tell another one important key point. So in this kind of, if in your expression this part comes in, a static 1 hazard occurs over there. You can have a concept like that also, because in your expression if this part is occurring, you can make sure of one thing, a static 1 hazard is available over there. We should try to rectify it like that. You can have it. Okay, so now the second step, what I am going to do is, K-map. So with this expression I am going to draw the K-map for it. So this is A, B, C. So like this, so 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 1. So we can see how it works. So this is for AB, right? So A is 1, B is 1. So A is 1, B is 1 where? Here. So here we can put 1. Then B dash and C. B dash and C. I is not available. So this one and this one. And in this came up, if you see, for AB we got this, for B dash we got this. B dash we got this, AB we got this, and I made this third term. So this third term, this is called as redundant value, and in normal K-map simplification you will neglect this, but here you are going to add it. So what happens is your y value will now become AB plus B dash C, this one, then this part is A should be there, then here the common term is C, so AC. So A and C is being added to neglect this error. So how come you are telling A and C is going to play a vital role in neglecting? We can see over here. Now I am going to add third term over here, that is A and C. Now what you did is you made a change with B, right? Because of that hazard occurs. We saw that. Now in this AC there is no B term, so my hazard will get neglected. What is the drawback of doing this is I am adding extra gate over here. So once you add the extra gate, it will of course take the space in any chip, and of course it will take some power too, and of course the switching time will be also more. So these are the drawbacks of adding this extra circuit. Okay, so this is what how to find the static 1 hazard and how to eliminate it. This is the way how you can eliminate the static 1 hazard. So I like to just map the static 0 hazard in the same manner over here. So then whenever if you are going to do for static 0 hazard, just what you are going to do, there are some more changes you want to make. Just convert this all to this and to or, then this to and. Okay, then the input first you give 0 and try to note down it, and in the expression also, if you see here, I said b plus b dash came, there you will get b dash. So okay, these are some hints that I want to tell. Anyway, you give a try of static zero hazard. Draw the circuit like this. Try to draw the timing diagram. Then try to get the expression for the circuit. Then do the K-map, and then redraw the circuit and make sure this works fine. So yeah, the same way, if you see, I'm getting b dash. Here in the expression also, instead of AC, I will get a plus c. This is product of sum. So there's a small difference. This is POS, this is SOP. So don't forget that also. POS a plus. So here after once finishing all the process, instead of this diagram, you will get like this. So done. Okay. Give a try for static zero. Now next we can go for dynamic hazard.